Learning outcomes. The objective is calculation of probabilities in business, thereby enabling us to reduce uncertainties in business and managerial decisions. After studying this module, you should be able to understand first, calculation of probabilities, second, select the appropriate law of probability to use in solving problems. Third, solve problems by using the laws of probability, including the law of addition, the law of multiplication, the law of conditional probability, and the law of total probability. Total probability and Bayes' rule revise probability by using Bayes' rule. Introduction. In module 1, we tried to define probability, discuss the basic concepts of probability, tried to understand and apply marginal, union, joint, and conditional probabilities, and discuss the different ways of assigning probability of an event. In business, we usually deal with not one, but two or more events. In case of two or more events, various laws of probability are used as tools to solve probability problems in business decision making. In the present module, which is module number 2, we shall discuss 5 laws of probability, which are the law of addition, multiplication, conditional probability, law of total probability, and Bayes' rule to quantify uncertainty. These laws provide a foundation for the scientific analysis of problems involving uncertainty. The laws of probability, the laws of additional probability. General law of addition, P bracket open x union y bracket shut is equal to Px plus Py minus P bracket open x intersection y, where x, y are not mutually exclusive events and x intersection y is the intersection of x and y. Special law of addition. If x, y are mutually exclusive, then P, which is probability bracket open x union y is equal to probability of x plus probability of y. Examples. Probability bracket open k or heart bracket shut is equal to P, which is probability of k plus probability of heart minus probability bracket open k and heart, which is equal to probability of k plus probability of h minus P bracket open k intersection h, where h is heart, which is equal to 4 divided by 52 plus 13 divided by 52 minus 1 divided by 52, which is equal to 16 divided by 52. These are not mutually exclusive events. Now, probability bracket open of k or q is equal to probability of k plus probability of q, which is equal to 4 divided by 52 plus 4 divided by 52, which is equal to 8 divided by 52, which are mutually exclusive events. The additional law can be illustrated with the help of a Venn diagram. Illustration 1, Venn diagram for two or overlapping events. In a city, 30% of the households read newspaper A, 50% of households read newspaper B, and 12% of the households read both A and B. What is the probability that a randomly selected household reads at least one of the newspaper? The following is the Venn diagram for two overlapping events. So, what we have is probability bracket open of A union B bracket shut is equal to probability of A plus probability of B minus the probability of AB, which is then equal to 30 divided by 100 plus 50 divided by 100 minus 12 divided by 100, which is equal to 0.68, or probability of AB in bracket epsilon plus probability of P A B epsilon plus probability of A and B, which is equal to 18 by 100 plus 38 by 100 plus 12 by 100, which again comes to 0.68. Now, let us look at the second illustration. Again, there is a Venn diagram for the three overlapping events. In a city, 30% of households read newspaper A, 50% of households read newspaper B, 12% of households read both A and B, 25% read India Today, which is a magazine, 5% read both papers plus India Today. Out of A readers, 20% read the magazine. Out of B readers, 32% read the magazine. Find the probability of a household selected at random reading at least one of these. Now, the Venn diagram for the three overlapping events, I repeat the Venn diagram for the three overlapping events. So, what we have here is that probability in bracket open of A union B union C bracket shut is equal to probability of A plus probability of B plus probability of C minus P bracket open A intersection B minus P, which is the probability bracket open of B intersection C minus again bracket open A intersection C plus probability bracket open of A intersection B intersection C. So, what we have here is probability of A plus probability of B plus probability of C minus probability of AB minus probability of BC minus probability of AC plus probability of ABC. So, what we have then is 30 divided by 100 plus 50 divided by 100 plus 25 divided by 100 minus 12 divided by 100 minus 16 divided by 100 minus 6 divided by 100 plus 5 divided by 100, which then equals to 76 divided by 100, which is 0.76. Now, probability again bracket open of A union B union C bracket shut is equal to P, which is probability bracket open of A epsilon B epsilon C bracket shut plus probability of B into A epsilon C epsilon bracket shut plus P again bracket open C absolute values of A and B plus P, which is probability bracket open of A B absolute value of C plus probability, which is P again bracket open of A C absolute value of B plus P bracket open absolute value of A B C plus P, which is probability of A, B, C. So, what we have is then 17 by 100 plus 27 by 100 plus 8 by 100 plus 7 by 100 plus 5 by 100 plus 1 by 100 plus 11 by 100, which again is equal to 76 by 100, which is equal to 0.76. The laws of multiplication. The general law of multiplication is probability of again bracket open x intersection u, which is equal to probability of x into probability of y divided by x, which is equal to probability y into probability x divided by y. The notation x intersection y means that both x and y must happen. The general law of multiplication gives the probability that both event x and event y will occur at the same time. For example, in a public sector undertaking, 60% of the workers are male workers, 30% of the men employed work part-time. If a worker is selected at random, what is the probability that a worker selected is a male worker and works part-time? So, the required probability is probability outside the bracket m intersection t, which is what we are trying to find out. So, probability again bracket open m intersection t is equal to probability of m into probability of t divided by m, which is equal to 0.60 into 0.30, which is equal to 0.18. So, it can be stated that 18% of the workers are male and they work part-time. If events x and y are independent, a special law of multiplication can be used to find the intersection of x and y. This special law utilizes the fact that when two events x and y are independent, that is the probability of x divided by y is equal to p into x and py by x, which is equal to py. Thus, the general law of multiplication states that probability, which is outside the bracket x intersection y, is equal to probability of x into probability of y divided by x becomes P, which is probability bracket open x intersection y, which is equal to probability of x into probability of y when x and y are independent. The special law of multiplication states that if x and y are independent, the probability of x intersection y is equal to Px into Py. For example, a class consists of 100 students, 30 of them are girls, 70 boys, 40 of them are rich and the remaining poor, 50 of them are fair complexioned. So, what is the probability of selecting a fair complexioned rich boy? The probability of selecting a boy is equal to 70 divided by 100, which is 7 by 10. The probability of selecting a rich person is 40 divided by 100, which is 2 by 5. The probability of selecting a fair complexioned person is 50 divided by 100, which is half. The probability of selecting a fair complexioned rich boy is then 7 by 10 into 2 by 5 into 1 by 2, which is equal to 14 divided by 100, which is 0.14. The laws of conditional probability. The conditional probability of x divided by y is the probability that x will occur given y. Conditional probabilities are computed based on the prior knowledge that the statistician has an idea of one of the two events being studied. If x and y are two events, the conditional probability of x is denoted as probability of x divided by y. This expression is read as that the probability that x will occur given that y is known to have occurred. An example of conditional probability is the probability that a person owns a Skoda car given that she owns a Ford car. This conditional probability is only a measure of the proportion of Ford owners who have a Skoda car, not the proportion of total car owners who own a Skoda. So, the conditional probabilities can be calculated with the formula given in the law of conditional probability. This formula is derived by dividing both sides of the general law of multiplication by the probability y. So, the law of conditional probability states as follows: the probability of x divided by y is equal to the probability of x union y divided by the probability of y, which is equal to the probability of x into the probability of y by x into the probability of y. Case study. In the study by Vidya-mitra consultancy to determine what changes in office design would improve productivity, 70% of the respondents believed noise reduction would increase productivity, and 67% said increased storage space would improve productivity. In addition, suppose 56 of the respondents believed both noise and increase in storage space would increase productivity, then a worker is selected randomly and asked about changes in office design. This worker believes that noise reduction would improve productivity. So, what is the probability that this worker believes increased storage space would improve productivity? That is, what is the probability that a randomly selected person believes storage space would improve productivity given that he or she believes noise reduction improves productivity? So, in symbols what it means is probability of S divided by N. That is what we have to find out. Note that given the part of the information is listed to the right of the vertical line in the conditional probability, the formula solution is that the probability of S divided by N is equal to probability of S intersection N divided by probability N. Pn is equal to 0.70 and the probability of S intersection N is equal to 0.56. The probability of S divided by N is then equal to the probability of S intersection N divided by probability N, which is equal to 0.56 divided by 0.70, which is equal to 0.80. So, 80% of the workers who believe noise reduction would improve productivity believe also that increased storage space would improve productivity. The laws of total probability. The law of total probability, also known as the law of elimination, is used when we want to estimate the probability of an event whose occurrence is dependent on the occurrence of some intermediate event in the experimental process. Let xi bracket open, where I ranges from 1, 2, 3 to n, be n mutually exclusive and collectively exhaustive events, and D be an event defined additionally on the sample space. Given that the marginal productivities, which is of Pxi, and conditional probabilities P, which is D divided by Xi, for all I are known, then the marginal probability of D is defined as, so the PD is equal to Px1 intersection D plus Px2 intersection D right up to Pxn intersection D, which is equal to P capital X1 into P D by X1 plus Px2 into P D divided by X2. This continues till probability Xn into probability of D divided by Xn. Since D could have resulted due to X1 or X2 or any way till Xn, we obtain probability of D by relating D with X1, X2 right up till Xn. Bayes theorem or the Bayes rule. The Bayes theorem or rule is a formula that extends the use of the law of conditional probability to allow revision of original probabilities with new information. Conditional probability takes into account prior knowledge about the occurrence of one event, say x1, to compute the probability of another event, say D, which is the result of additional information. However, this D could have been resulted due to x1 or x2 or any way up till xn. So, in some practical situation, a decision maker may know that another event, that is D, has occurred, and he has to find the cause of happening of that event. That is, he has to decide whether the occurrence of D is due to x1 or x2 or any way up to xn. So, the decision maker cannot use conditional probability rule directly to revise the probabilities for this decision. Bayes' theorem, which is based on prior information or knowledge, enables the revision of probabilities to determine the particular cause of happening of that event. According to Levine, Bayes' theorem is used to incorporate additional information as it is made available and helps create revised or posterior probabilities. We may state Bayes' theorem formally as follows. So, if x1, x2 right up till xn are mutually exclusive and collective exhaustive events with non-zero prior probabilities with respect to a random experiment, and if D is any sample outcome in the sample space of the said experiment such that probability D is greater than 0, then the posterior probability of an event x1 given D is. So, the probability of xj divided by D is equal to probability of xj intersection D divided by probability of x1 intersection D plus probability of x2 intersection D, which continues right up to probability of xn intersection D, which is then equal to probability of xj into probability of D divided by xj divided by summation of probability xj multiplied by probability of D divided by xj, where j is equal to 1, 2, 3 right up till n. This is equation 1, where the denominator is the probability of the sample result and probability D, and the numerator is a specific term of the denominator. Bayes' theorem is found to be useful in real life problems. The mathematical steps leading to the general formula of Bayes' theorem with the help of a mini case study are given below. Now, let us look at the case study. An export house manager purchases cotton shirts for an export consignment from two designers. Suppose designer A produced 65% of the shirts and designer produced 35%. 8% of the shirts produced by A were defective and 12% of the B designer's shirts were defective. So, on a particular day, a normal shipment arrives from both the designers and the contents get mixed up. A shirt is chosen at random for quality check by the authority and is found to be defective, and thus the consignment is rejected. Now, what is the probability that designer A produced the shirt or that designer B produced the shirt? The decision is required by the exporter to take corrective measures to reduce the probability of rejection of his consignment in future. Here we are given data on the percentage of shirts produced by the two designers, which provides basis to know the likelihood that a random selected shirt is produced by a particular designer. The given information shows that if we let x1 represent the event that designer A produced the shirt and x2 represent the event that designer B produced the shirt, then from the given data we have Px1 is equal to 0.65, Px2 is equal to 0.35. These values are called prior probabilities. They are so called because they are established prior to the empirical evidence about the quality of shirts. As per the quality of shirts, the conditional probabilities show: 1. That the probability that the shirt is defective on the condition that it is produced by designer A is probability D divided by x1, which is 0.08. Similarly, probability of D divided by x2 is 0.12. The terms probability D divided by xj are called likelihoods. From the given data we know that probability of x1 is equal to 0.65. The new information that the shirt is defective changes the probability. With this additional information, we can revise the probability that the shirt was produced by designer A. Let D be the event that the tested piece is defective, and we want to know the probability that the defective shirt came from designer A. We now want to determine the probability of x1 divided by D and not just Px1. Thus, after the additional information experiment is performed, we now replace probability xj by Pxj divided by D. So, what we have now is probability x1 divided by D, which is equal to probability of x1 intersection D divided by probability of D, which is equal to Px1 multiplied by Px1 divided by D, the whole thing over Pd, which is again equation 1. However, Pd is not readily discernible. This is where Bayes' theorem comes in. There are two ways the shirt may be defective. It can come from designer A and be defective, or it can come from designer B and be defective. So, using the rule of addition given below, Pd is equal to Px1 intersection D plus Px2 intersection D, which is equal to Px1 multiplied by Pd divided by x1 plus Px2 multiplied by Pd divided by x2. This is second equation. So, substituting Pd from the second equation in the denominator of the conditional probability formula in the first equation, Bayes' theorem tells us that Pxj divided by D is equal to Pxj intersection D divided by Px1 intersection D plus Px2 intersection D, which goes up right to Pxn intersection D, which is then equal to Pxj into Pd divided by xj. This whole thing over summation of Pxj into Pd divided by xj, where j goes up from 1, 2 till n. We again call this equation 1, where the denominator is the probability of the sample result, Pd and the numerator is a specific term of the denominator. So, we can find probability of x1d as probability of x1 divided by d, which is equal to probability of x1 intersection D divided by probability D, which is equal to probability of x1 intersection D divided by probability of x1 intersection D plus probability of x2 intersection D, which is equal to 0.052 divided by 0.094, which is equal to 0.553. Px2 divided by D is equal to probability x2 intersection D divided by probability D. This is then equal to probability of x2 intersection D divided by probability x1 intersection D plus probability x2 intersection D, which is equal to 0.042 divided by 0.094, which is equal to 0.447. Thus, in the above case, the probability was 0.65 that the shirt was produced by designer A and 0.35 that it came from designer B. These are called prior probabilities because they are based on the original information. The new information that the shirt is defective changes the probability with the result of a sample of a defective shirt. So, the probability of x1 has been revised down to 0.553 and that of x2 has been revised upward to 0.447. One way to lay out a revision of probabilities problem, which is the Bayes rule, is to use a table which shows the analysis for the shirts problem. So, we have the following table where we have the heading of the columns as event, the second one prior probability, the third conditional probability, the fourth joint probability of P intersection D and P probability of B intersection D respectively in the following, and the last column is posterior or revised probability that the defective shirt was produced by A or by B. Under the event, we have designer A and designer B. Under the heading of the second, which is prior probability, we have Px1 which is 0.65 and Px2 which is 0.35. Under the third, which is conditional probability, we have probability x1 divided by D, which is 0.08, and we have P probability of x2 divided by D, which is equal to 0.12. Then we come to the next, which is the joint probability. In this, we have probability of x1 intersection D, which is equal to probability x1 into probability D divided by x1, which is equal to 0.65 into 0.08, which is equal to 0.052. And the last one is the posterior or revised probability that the defective shirt was produced by either A or B. Here you have the probability x1 D, which is equal to probability x1 intersection D divided by probability D, which is equal to 0.052 divided by 0.094, which is equal to 0.553. Right, that is for designer A, and for designer B it is equal to probability x2 D, which is equal to probability x2 intersection D divided by probability D, which is equal to 0.042 divided by 0.095, which is equal to 0.447. Right. So, to compute the fifth column, the posterior or revised probability involves dividing each value in column 4 by the total of column 4. For designer A, out of the total of 0.094 that are defective, 0.052 of the total shirts out of designer A. Dividing 0.052 by 0.094 yields 0.553 as a revised probability that the defective shirt was made by A. This probability is lower than the prior or the original probability of 0.65 because fewer of A's shirts as a percentage are defective than those produced by B. The defective shirt is now less likely to have come from A than before the knowledge of the defective shirts. B's probability is revised by dividing the joint probability of the shirt being made by B designer and defective 0.042 by the total probability of the shirt being defective, which is 0.094. The result result is 0.042 divided by 0.094, which is equal to 0.447. The probability that the defective shirt is from B designer increased because a higher percentage of B shirts are defective. Summary. In the present module, which is the second one, we learned that various laws of probability are used as a tool to solve probability problems in business decision making. These laws provide a foundation for the scientific analysis of problems involving uncertainty. We discussed 5 laws of probability: law of addition, multiplication, conditional probability, the law of total probability, and Bayes' theorem. The law of addition, the law of multiplication, and the law of conditional probability to calculate probabilities of 2 or more events and to quantify uncertainty. The law of total probability, also known as the law of elimination, is used when we want to estimate the probability of an event whose occurrence is dependent on the occurrence of some intermediate event in the experimental process. Bayes' theorem or Bayes' rule is a formula that extends the use of the law of conditional probability to allow revision of original probabilities with new information.